Everyone, welcome to this talk on FO-Complete program verification for heap logics. This is joint work with Adithya Murali from the University of Wisconsin-Madison and Aaron Councilman and P. Madhusudan from the University of Illinois Urbana-Champaign. So let's begin. We are interested in proving properties about programs that can destructively modify a heap. In this setting, we would like to prove Hoare triples of the form pre-prog-post, which says that if we begin at a state with the heap as described by the precondition and run the program, then the heap gets transformed into a new heap that satisfies the post condition. For instance, the precondition here says that the original heap can be split into two disjoint lists pointed to by x and y. If the program is run, this heap gets converted into a new one such that the resulting heap is a list whose head is ret and whose keys are the union of the keys of the original two lists. However, expressive heap logics are inevitably incomplete. Checking the validity of triples is not only undecidable, but not even recursively enumerable. That is, there is no procedure that, given a valid formula, will terminate and say valid. And there are several reasons why heap logics are incomplete. One, many heap logics are defined over only finite heaplets. Second is quantified combinations of theories. Third, they use second-order quantification. For instance, to talk about disjointness, one might write, there exists two disjoint heaplets where each one is a list. Finally, data structures are defined recursively using least fixed point semantics. Our goal is to build complete procedures. In this work, we design logics to address the sources of incompleteness in various ways. One, note that first-order logic is complete over arbitrary models. However, even if we restrict ourselves to finite models, even it already becomes incomplete. As such, our logics will be over arbitrary heaplets, that is both finite and infinite. Second, we only allow quantification over heap locations. Third, we use unique heaplets to avoid second-order quantification. Finally, and unfortunately, the incompleteness due to least fixed points is not negotiable. Even the simplest extension of first-order logic with a least fixed point operator is already incomplete. Despite this, we would like to have some theoretical guarantee for completeness, and the guarantee we use is called FO-Completeness. FO-Completeness. The idea here is to ask for a complete procedure when recursive definitions are interpreted as any fixed point instead of just the least fixed point. Let's quickly look at the difference between least fixed points and fixed points. A list defined over least fixed point semantics would intuitively be locations that can reach nil via a bunch of next pointers. When interpreting it over fixed point semantics, it's simply some function constrained by the definition on the right. In particular, an infinite chain where x1 points to x2 and so on, where list of xi holds for every xi will satisfy the fixed point definition, but not the least fixed point definition. So by this abstraction, we are expanding the set of models that can satisfy a formula. Now, FO-completeness is desirable for several reasons. First, if a formula is valid for fixed point semantics, then it's in particular valid for least fixed point semantics. Second, if the original logic is first-order logic plus least fixed points, then the abstracted logic is just first-order logic again, which is complete. This is nice because many automated reasoning tools we have are first-order, and FO-completeness makes statements amenable to reasoning using such solvers. In fact, it's been shown that several practically efficient techniques that unfold recursive definitions are FO-complete. And this leads us to the goal of our work, which is, can we design heap logics with recursive definitions that have FO-complete and practically efficient verification procedures? And the answer is yes. The first logic we look at is frame logic, which was introduced by Murali et al. In 2023. This is a first-order logic with implicit heaplets that can be converted into first-order logic with least fixed points. We provide verification condition generation, reducing this to FO plus least fixed points for a frame logic fragment for which thrifty unfolding of recursive definitions is FO complete. Second, we define a new separation logic, SLFL. Separation logic was introduced by O'Hearn et al. A long time back. Such logics are typically second order, but ours has an alternate semantics that makes it translatable to first order logic plus least fixed points via frame logic. Let's look at frame logic. The key design decision here is to have heaplets be determined by the formulas. The heaplet of a formula is computed via a support operator. Intuitively, the support of a formula are the locations one needs to dereference to evaluate its truthhood. For instance, the support of a list will be exactly the locations in said list. And this has several nice properties. Firstly, it avoids second order quantification. Since heaplets are captured by support, we can say two lists are disjoint if the intersection of their supports is empty. Second, it's been shown that frame logic readily converts into first order logic with least fixed points. Furthermore, by restricting to only one-way functions, that is, functions can go from the heap to a background sort, but not the other way around, we obtain a fragment of frame logic for which we can do a thrifty unfolding of recursive definitions. And this technique is FO complete. And we'll be working with this fragment. The frame logic verification pipeline is as follows. We take a program annotated in frame logic, and it generates verification conditions in first order logic. This is then sent to a natural proof solver, which does quantifier instantiation and unfolds recursive definitions to prove validity. This mechanism is complete for first order logic, even with background theories, if we restrict it to a one-way fragment, as shown by Loading et al. In 2018. And we use inductive lemmas to bridge the gap between fixed points and least fixed points. As for the VC generation itself, we use a strongest post style method to generate VCs. We step through the program, track the program transformation and accessible memory. We collect frame rules and information about the heap. And of course, we need to make sure all of these fall into the correct fragment. And when designing a VC generator, we also have to take care of memory safety during dereferences and ensure that function calls access only the implicit heaplets defined by its precondition. For this, we use a relaxed post condition, which relaxes the heap condition by simply asserting that the heaplet of the precondition of the call is contained in the allocated memory, as opposed to it being equal. Function calls pose other issues as well. When handling function calls, the contract of the call tells us that the heap described by the precondition is transformed to one that satisfies the post condition. And using this info, we can have the portion of the heap that the call modifies. And we also have to generate frame rules reasoning about the recursive definitions whose supports are not changed. And if the support is unchanged, then the recursive definition will also remain unchanged. And these last two also introduces quantifiers, which have to be instantiated in a succinct way. We do this by tracking a set of relevant locations as we generate the VC and instantiate quantifiers only on these. We now move on to our separation logic, SLFL. Recall that a source of incompleteness of separation logics is the use of second order quantification over heaps. A formula list x star list y is defined as there exists two portions of the heap such that list x in H1, list y in H2, and the two heaplets H1 and H2 are disjoint. And to avoid this, we introduce a new separation logic, SLFL, which is inspired by frame logic. Just like frame logic, we require unique heaplets, that is, formulas holding at most one heaplet, which avoids the existential quantification mentioned earlier. This is captured using supports, which is similar to supports in frame logic, which capture the locations in a heap that are relevant to the formula. The semantics differ from typical separation logic to obtain unique heaplets. For instance, true is satisfied if the heap is empty instead of being true for all heaps. Disjunction simply asks the heap to be the union of the supports of the two formulas A and B, instead of saying that the entire heap is either the support of A or that the entire heap is the support of B. And these choices allow us to translate SLFL to frame logic. We have incorporated an SLFL to FL translator into our VC generation tool. SLFL annotated programs are converted to FL, and this is followed by the usual VC generation pipeline. We've tested our verification tool on a suite of benchmarks, annotated in both frame logic and SLFL. We noticed that frame logic is faster across the board, and the translation from SLFL to frame logic incurs some bloat, but all benchmarks go through in reasonable time, in less than a minute. To conclude, we identified two heap logics, frame logic and SLFL, with recursive definitions with an FO-complete and practically efficient verification procedure. We use FO-completeness as a new yardstick for heap logics, from having no guarantees because logics are inherently incomplete to having some guarantees. This ensures verification methods don't resort to just heuristics that may fail even though they have simple proofs. In our case, any theorem valid in fixpoint semantics will be proven. And in fact, many solvers already use a thrifty unfolding technique we use in our approach. I think time is up, right? For future work, that's it. I can talk about it more offline if you want. Yes.